Hello friends, here in this video we will see an expression of differential equation for deflection. That is, here we are going to derive a formula which we would be using in Macaulay's method as well as in double integration method. So for that, here we have a diagram. Now in this diagram, in this red color which we are seeing, this red portion, it is the length of arc AB which I am considering as a part of a bent beam. That is, when the beam gets bent, from that I am taking a small section which is AB. Next, this small section AB has a length ds. At point A, I am drawing a tangent joining it to the origin. The angle is psi. Next, if I join point B, draw a tangent to it, then the angle formed is psi plus d psi. Next, point A is connected to C. Similarly, B is connected to C, which is the center for this arc. Then R is the radius of curvature of this bent beam, and here the small angle is d psi. That is, since we have taken the small length ds, here we are having small angle which is d psi. So whatever is there, first I'll define these terms. I'll say that in the derivation part, let ds be equal to small length of bent beam considered. Here I have taken the small length of the beam as ds. Next, C is the center for bent beam arc. Next, capital R is the radius of curvature of beam AB. Then psi is the angle made by point A of beam with horizontal. Then psi plus d psi is the angle made by point B of beam with horizontal. Next, we have dx and dy. Here this arc ds which we are considering, then it is having points A and B. Now when I am drawing a horizontal and vertical line through that, I get AD as dx distance, then BD is equal to dy, and here we are forming a right angle triangle. Next, d psi, it is the angle made by beam capital AB with respect to center C. So now, once I have defined all the terms which I am going to use in this derivation, we can start with the derivation part. Now, this derivation of expression for differential equation for deflection, as I have told, it will help us in double integration method as well as Macaulay's method. So now, when we are starting with the derivation, first is I'll consider this angle ACB, which is d psi. So I'll start it in this way, that since angle ACB is equal to d psi, next I'll find the length of this arc ds. So therefore, length of arc, which is arc AB, is equal to ds, and that is equal to the angle d psi multiplied by radius. So it is d psi into radius, because here we want the length of arc. So this length of arc AB will be the radius multiplied by the angle. So it is r into d psi. Next, therefore, for this term which I am getting here, I'll shift r in the denominator. So I have ds upon r is equal to d psi. Therefore, I will shift ds in the denominator. So here I have 1 upon r is equal to d psi by ds. Now I will keep this as my equation number 1. This will be equation number 1 for us, and this we have got from the length of arc. Now after this, since the length of arc which we are considering, it is in the form of an arc and it is having a very small length ds, so this can almost be considered as a straight line instead of an arc. So I'll consider this right angle triangle ADB. So the next step would be, now considering right angled triangle ADB, now in this the angle is made here, which is nothing but it is equal to psi. So I'll mark angle as psi. Then AB is nothing but ds, AD is dx and BD is dy. So I'll mark them. This is ds, here we are having dx, and this is equal to dy. So I'll say that if I have considered this triangle, then here I will get, first of all, tan psi will be equal to opposite by adjacent, that is BD upon AD. So therefore if I put the values, tan psi will be equal to BD is dy and AD is dx. So I am getting the first relation here, keeping this as equation second. Next, from the same triangle I'll get another relation, that cos psi will be equal to adjacent side AD upon hypotenuse side AB. So therefore cos psi will be equal to AD is dx and AB is ds. So I'll keep this as equation third. And similarly, once I got cos psi, now I will make this reciprocal. So I get sec psi, and which is opposite of cos. So here I will get ds by dx. This I will keep it as equation number 4. So now, once I have written all the formulae, all the relation here, now I am going to differentiate equation number 2. So I'll say that onto the next page. Therefore, differentiating equation number second with respect to x, we get, now here we are having in equation second tan psi. So if I differentiate it, it becomes sec square psi. So therefore we have sec square psi d psi by dx is equal to, on the right hand side we have dy by dx. So once we differentiate it, it becomes d square y by dx square. Now once I have reached here, then I will keep sec square psi as it is. D psi by dx, it can be written as d psi upon ds into ds upon dx is equal to d square y by dx square. Here simply I have multiplied by ds and divided by ds. So once they get cancelled out, I will get this same term. Now after this, here I can say that ds by dx from equation number 4, it was sec psi. So therefore I'll keep sec square psi as it is, d psi by ds also as it is. Now in place of ds by dx, I'll put sec psi. Now therefore sec square psi into sec psi, that becomes sec cube psi, and here I am having d psi by ds. So d psi by ds can be written as, from equation number 1, I can replace d psi by ds with 1 by capital R. So here I am replacing d psi by ds by 1 upon capital R, and previously where I have written ds by dx is equal to sec psi, here I can write down, refer equation number 4. And next, now after reaching here, I will keep 1 by r on one side. So keeping 1 by r on one side, here I have d square y by dx square. Sec cube psi will be written in the denominator because here it is getting multiplied. So here I have sec cube psi. Next I'll write it in another form. So therefore 1 upon r will remain as it is, d square y by dx square will remain as it is. Next in the denominator I can write that as sec square psi bracket raised to the power 3 by 2. Here what I have done is, since sec cube psi, it can be written as sec square psi, and then I am multiplying it by 3 by 2. So when this term it gets multiplied, that will be sec square psi into 3 by 2. So 2 and 2 gets cancelled, so I have the same term sec cube psi. So sec cube psi can be written as sec square psi into the bracket raised to power 3 by 2. Now I'll say that this term will be equal to d square y by dx square divided by sec square psi can be written as 10 square psi plus 1 raised to the power 3 by 2, since sec square theta is 10 square theta plus 1. Now therefore I will write 1 by r as it is, that is on the left hand side. On right hand side in the numerator it is d square y by dx square. Next here in the denominator I'll write this as 1 plus now 10 square psi. In equation number 2 we have 10 psi as dy by dx. So 10 square psi will be d square y by dx square. So therefore here I can write this as dy by dx because that is 10 psi value and it is square, and this is raised to the power 3 by 2. I'll say that refer equation number 2 because there we had 10 psi is equal to dy by dx. So just I have replaced tan psi with dy by dx. Now after this I can say that since dy by dx is called as the slope and here we are taking the square term, so since we have a very small length of the beam considered, which is ds, a very small length, and for that the slope is d square y by dx square. The slope is really small, so, and we are taking the square of that, so this denominator is very small. So I'll write down, since the denominator is very small, so I'll write down, therefore neglecting the term dy by dx square, we get, so once I neglect this term, then the denominator becomes 1, so I am left with 1 upon r is equal to d square y by dx square. Now I will keep this as equation number 5. Then after reaching here, I'll say that from the flexural formula, the flexural formula was m upon I is equal to sigma b upon y is equal to E by R. Now instead of using the complete formula, I'll use only the terms m upon I is equal to E by R. So next, therefore I will bring E onto one side, so I have m upon EI is equal to 1 upon R. So this will be equation number 6. Now I am going to compare. In equation 5 we have 1 upon R is equal to d square y by dx square. In equation 6 we have m upon EI is equal to 1 upon R. So from both the equation 1 upon R gets cancelled out. So therefore from equation number 5 and 6 we have d square y by dx square is equal to m upon EI. Next I will keep m on one side, so therefore m is equal to EI will be shifted onto the other side, d square y by dx square and this will be my equation number 7. So now I can say that in equation 7 I am getting the equation of bending moment. So therefore from equation number 7 we get a differential equation from which we can calculate slope and deflection by using Macaulay's method or double integration method. So once we have derived the equation of bending moment, m is equal to EI d square y by dx square, then after this when we will take integration of this equation, then we will be getting dy by dx, because integration of d square y by dx square is dy by dx, and that dy by dx is called as slope. After that if I integrate it once again, that is integration of dy by dx will be y, that is called as deflection. So just by using equation 7 we can get both slope and deflection, hence this equation would be used in the calculations of slope and deflection at various points in a beam, and as I have mentioned we can use them in Macaulay's method as well as double integration method. So in this video we have seen the expression for differential equation for deflection.